Okay. So this slide, I think I'm repeating for the third time. This is the, I guess, uh, ImageNet Large Scale Visual Recognition Challenge, which happens every year, and it has a lot of, the dataset itself has a lot of classes and a lot of images, but the classification task has exactly 1,000 categories, 1,000 classes, and 1.5 million images. And this was the improvement that was seen after 2014. Actually, there are a couple of improvements as well, 2015 and 2016. Mostly from 2013 or 2014 onwards, it's been dominated by Google and probably even Microsoft. But before that, at least 2012 and 2013 was from the academia, and the jump from 2011 to 2012 was a CNN that we're gonna actually look at a couple of times later on in this lecture. Okay, so why are we studying CNNs? Because of this jump. Okay, or you can be more recent. So this is today's article. Actually, you can see 20th January. So this is an article which appeared in Nature. So this is about dermatologist level classification of skin cancer with deep neural networks, and they basically just not just use, but they basically use convolutional neural networks to achieve the state-of-the-art result. Okay, so this is a good group from Stanford. So you can see an example. Impactful outcome from learning or at least knowing this tool of this generation, right? Okay, so CNNs are very similar to feed-forward neural networks in the sense that each neuron is still associated with a bunch of weights and a bias. So what does a neuron or a node do? It receives input, okay, from the previous layer, or when I say input here, I'm just saying it receives something from the previous layer. The previous layer can be a hidden layer or the input layer. It performs a dot product of vectors, okay, and probably even adds a bias and then applies nonlinearity. That's what a node does. And the key difference that we're going to kind of see in this lecture is that CNN attempts to reduce the number of parameters. Okay. The parameters are essentially number of parameters. What do you mean by number of parameters? I'm just saying. Okay, this is too far. So number of parameters just count the number of scalars in this parameter set. Okay. So maybe this is 100 cross 100 dimensional. Then there are 10 to the power 4 parameters here. And maybe this is 100 dimensional, so you can just add those numbers and that will be the number of parameters. So we are going to reduce the number of parameters using a CNN. Okay. So revisiting again feed-forward neural network. So the neural network itself gets a vector xi and transforms it into a score vector, right? So xi is the ultimate input on the left-hand side, and at the end of at the end of its computation, the network itself is just going to output a score vector. If it's 1,000 classes in ImageNet, it's going to output a 1,000 dimensional vector. If it's a 10 class data set, then it's going to just output a 10 dimensional vector, right? And each hidden layer has neurons, and that's what we saw earlier. And this is what I explained earlier as well. Each neuron is fully connected to the previous layer in this architecture, a feed-forward architecture. So in terms of diagram, these are inputs either from the input layer itself or from the previous hidden layer. Okay, all the scalar computations that are done by previous neurons are the inputs. Okay, input coordinates. They are being multiplied by weights. So these are actually just the rows of the W matrix. Okay, if you're doing, so I said W times max of 0 comma some input. Let's say it could be hidden layer or it could be the input itself plus B. So this was the vector notation. But what was an individual neuron doing? Individual neuron was just taking was just computing on one row of this W matrix. So this time this is actually just a vector. This is an element-wise operation. So this is the X, right? There and plus, yeah. So let's say this is B1 and this is W11, W1J. Sorry. Oh, sorry. I don't know how to do this. I think they're using the transport notation. Okay, let me use this notation. And let's say it's okay. This is the computation that is being done by a single neuron, right? And that's being diagonally represented over there. Actually, there it's n-dimensional, here it's t-dimensional, but you get the idea. So each neuron is just associated with a single row of your weight matrix if you're thinking of it that way. And this is a picture we have seen several times already. Now, so why I'm trying to recap feed-forward neural networks is because you'll see that CNNs are very similar to them except for a couple of changes. So let's now fix a particular type or particular domain where CNNs actually shine, which is going to be the domain of vision or images. So this is the what is called the CIFAR10 dataset, and you will probably use that in your assignment. Here the images are 32 cross 32 dimensional. When I say 32 cross 32 cross 3 dimensional, it's just 3 matrices next to each other, where each matrix is of size 32 cross 32. Okay, so this picture that you're actually seeing visually is just a 3-dimensional array, okay, of numbers, where each entry in that 3-dimensional array is a number between 0 to 255. Okay. Okay, so now let's think about how many parameters, how many number of parameters would I need. So the first fully connected feed-forward neuron, let's say I have the 2-layer network. The first neuron in the hidden layer would need to have 32 times 32 times 3 weights associated with it, plus 1 bias parameter. Is that clear? Okay. So what if I scale up the images to something which is realistic, from your webcam or from your camera or from your phone? The size of the images are definitely going to be greater than this. So you can see that the number of weights associated with a single neuron is too many, right? And that's the point that we are trying to make here. So now and CNNs are going to actually reduce the number of parameters. So we saw for a very, very small image, it's probably the size of an icon in your web page or something like that, right? So it's very small, but it needs a lot of parameters, and so we're going to try to reduce the number of parameters. So let's now transform our perspective of how an FNN or feed-forward neural network looks like, so that we can motivate the CNN. So this is what is the diagram. Now I'm going to try to look at it from a different point of view, and this is shown on the right side. I'm drawing this picture, and that picture is motivated by two things. One is we have images, which are inherently, you kind of look at it as a 2-dimensional object. So let's just rearrange all these neurons, kind of put them in a square. This is just a linear stacking of the neurons. Maybe I'll put them next to each other in a squarish fashion. Okay, that's all I'm doing. So what does it mean? So each neuron is still connected to every other coordinate, or every coordinate of this input image, right? In this case, so it's connected to 32 cross 32 cross 3, for example. And in the 2-day, because it's a 2-layer feed-forward neural network, this neuron, all the neurons here are connected to a single number here. Okay. Of course, there is a nonlinearity operation at every coordinate on this side as well. So that's the perspective I want to bring. This is the same as this, except I've brought in a 2-dimensional aspect to it, right? So the first new idea is going to be that we're going to have these layers have depth, okay? And depth does not correspond to the number of layers in the network. Here we're going to talk about the depth of a layer rather than the depth of a network, okay? So here there's no notion of depth, or the depth is trivially 1 unit, for example, right? Except for the images. Images have 3 colors, but you can kind of think of think of a grayscale image, right? It just has depth 1. The hidden layer, there's really no notion of depth. I just said I'm just going to rearrange them as squares. The depth is just 1, right? But now what will happen is our layers will have depth, and so the layers will start looking like this. Okay, so we're going to start understanding CNNs from a layer point of view, and then we'll get to what is inside a layer. And inside a layer, of course, it's going to be neurons, which are we'll get to the neurons later. Okay. So when a layer looks like this, how does the output look like? Remember, layer is just is a proxy for all the neurons just arranged in a spatial manner, right? In this case, there's a width and a height. All the neurons are arranged like this. Each neuron is just outputting a single number, right? Max of 0, its input, which is that linear combination. So output will also look like a 3D volume. It's going to look like a tensor, okay, a 3-dimensional array. So when you're talking about a layer or its output, it's basically the same thing in terms of visualization. Of course, we're not looking at the numbers, we're just looking at the shapes here. So input has dimensions this much in this case, and final output has a dimension, because 2 of the dimensions are trivially 1, 1, and CIFAR 10 has 10 classes. The output has a dimension which is this. Okay. So assuming 2 hidden layers, previously we had this, which I just changed into kind of a width plus height representation, which was this. Okay. So basically you had a flat volume like this, which kind of got transformed into a hidden layer, got transformed into another hidden layer, and finally got transformed into a score vector. Okay. And these need not be smaller; this can be even larger than the input. But I've just shown that they could be potentially of different shapes. For example, this can be 100 cross 100. This probably was maybe 50 cross 50. This was probably something else. Okay. But now our CNNs will start having depth, so they look like this. So initially maybe 32 cross 32 cross 3, but now it will be something else and something else, which will constitute neurons, and ultimately we'll still get a score vector, which is 10 cross 1 cross 1 cross 10. Yeah.
So when you're converting the 2-layered hidden layer into a 3-layered, 3-dimensional hidden layer, are still all the neurons from the input image connected to all the 3 dimensions of all the multiple layer depth, all the depth neurons?
So there is no depth here for the feed-forward network. There is no depth. Yeah, we'll get to how they're connected later. So we haven't yet looked into the shape, the 3-dimensional object here. We are just arranging them by layers, and we are showing the first difference between a CNN and a feed-forward neural network. That there is this notion of depth. So instead of a natural way to for at least images domain, a natural way to rearrange or represent this feed-forward network is in terms of, okay, because the image has both the 2-dimensional entity, let me kind of plot it in this way, represent it in this way. All I'm saying is that now we're going to look at CNNs which will have depth. How the neurons are arranged internally we'll get to in a couple of slides. Okay.
So the output is going to be the same vector?
Yeah, output is still the same. Let's say it's 1 cross 1 cross 10 for the CIFAR 10, or it's only 1 cross 1 cross 1000 for ImageNet classification task. Input is still 32 cross 3, for example. Yeah. So what we try to understand is, what are the properties that I'm going to first classify these layers as certain types. Okay. First, I'll have a certain layer called the convolutional layer. Second, I'll have a particular type which is called the pooling layer. And third is a type which is the fully connected layer. Okay. Fully connected layer is actually just the same as the feed-forward neural networks layer representation. So it will not have a depth. So basically, it will just be a depth of 1, trivial depth. Okay. And we're going to stack these layers in various ways. Okay. So let's say it's really CIFAR 10 that we're working with. Then let an example architecture be as follows. We have an input. I'm going to put some layer. I'm going to tag it as a convolutional layer. And then I'm going to put another layer. I'm going to call it a pooling layer. And then I'm going to put a third layer, which is the fully connected layer. Okay. So here I have 3 layers stacked next to each other. Okay. So input. So this layer is nothing but the CIFAR10's input data. So it's just 32 cross 32 cross 16 dimension, right? So what does the convolution layer, input output look like? Convolution layers will still have the neurons. So this is the layer which will have neurons, okay? And the neurons compute just like how they compute in the feed-forward network. In the sense, they're going to get a bunch of inputs. They'll have a bunch of weights associated with them, and they're just going to multiply the weight with an input, just sum them up, add a bias, and output a transformed version of it, which is just a nonlinear, just pass it through a nonlinearity and get the output. So that's what a neuron will do. That's what a neuron does in a feed-forward network, and that's what a neuron is going to do even here. But the interesting thing about convolution layer is that it may output a different shaped tensor or a three-dimensional array. For example, let's say the input is this, output is going to be 32 times 32 times 12, let's say. So why this 12? We'll look at it. It's just an example. Okay. So out of these three layers, convolution layer will have neurons, the regular neurons that you saw before, or nodes. Sorry. Fully connected layer will also have the same nodes as you saw, a few slides before. So what does the pool layer, do? It performs a downsampling in the spatial dimension. Okay. So what does downsampling mean? You have a tensor, right? I have a big tensor, which if you in terms of diagram, it's just a box, right? It has a width, a height, and a depth, right? So this is the input of the pool layer, and it's going to output some other tensor, okay, which is going to be smaller. Some width prime, some height prime, and the same depth. So it's going to just maintain the depth, but it's going to just downsample. Let's say there are x, y, z, and w here. There are 4 numbers on this coordinate or this dimension of the 3D array. It's going to output something else, some alpha. Okay. Downsampling means just instead of 4 numbers, I'm going to use 1 number, something like that. So we'll get to downsampling actually. So it's just a prelude to what's going to come later. So the result of the downsampling operation is if the input is of certain size, the output spatial dimensions get reduced. Okay. If I do downsampling by 2, then it just divides by 2. Okay. Output tensor size is shrunk in the spatial width, height dimensions. It hasn't changed in the depth dimension. Okay. And the fully connected layer, as I said, is fully connected, and therefore input can be any tensor, let's say 16 times 16 times 12, but it doesn't matter to the layer itself because the tensor has depth or not. The output will have. In this example, the output will have is supposed to output the score vector, and so output will definitely be a 10-dimensional score vector. And since it's fully connected, all the this tensors is connected to every neuron. In the sense, whatever number of values are there here, it's connected to every neuron in the fully connected layer. Okay. So at the high level, what's happening? We went from pixels, which are these pixels, to scores, which are 10 in number, and we went through these layers. The layers which have parameters are the convolution layer and the fully connected layer, because these are the ones which have neurons, right? The neurons are the ones which are associated with the weights, right, or biases, as well as nonlinearity. Nonlinearities can also have parameters. Pool layer typically does not have a parameter, so we'll look into that as well. And basically now again the operation is the same as what you did in the feed-forward neural network. So you have to optimize these parameters such that you achieve scores consistent with what you have in your training data. Okay. So in terms of layers, is there any confusion? We'll get into each layer in depth so that it's clear. But at the meta level,
is the width and height maintained in the convolution there, or does this?
It doesn't have to be. I think in this example I just wrote that it's being maintained, which was this width and height was the same as the input, but it doesn't have to be. We'll get to that detail as well. What?
If you can alter the width and height.
Yeah.
Convolution
So why is even any layer needed here? It's not clear. I mean, how is it reducing the parameters? How is any of these layers different from what you've studied before? It's not clear yet. I'm just talking about a layered view of this function where a function is basically being looked at as a sequential operation where each intermediate part of the function is getting some tensor as input, some tensor as output, right? That's what we are just seeing here. We'll get to why these layers make sense and why these layers help in doing better classification. Yeah.
How does the downsampling work? Like for example, 2 cross 2, how does it get reduced to 1?
Yes, so we'll go into the detail into a detailed example in a few slides, maybe half an hour from now. So I'm just trying to illustrate the property of the layer that pooling does something like downsampling. We'll study downsampling in a few minutes from now. Convolution layer, it's not clear what it does yet, but it at least preserves. It doesn't preserve anything. So we'll now study what convolution layer actually does. But at least we know that it has neurons. Okay, pooling layer doesn't have neurons. Convolution layer has neurons. That's the only thing we have revealed so far, right? Okay, so I'm slowly trying to introduce additional objects which will be important. So let's look at convolution layer now. Okay, so the layer's parameters, since the layer is a bunch of neurons, it will have weights, right? But now we're going to call these parameters, we're going to kind of look at these parameters as sets of filters. Okay. There's two new definitions or two new objects, a set and a filter. A set, of course, you can kind of understand. Set is just a collection of something. Filters. What is a filter? A filter is just a linear function parameterized by a tensor. Okay. So filter is something, it's just a new name for something you've already seen. A filter is nothing but okay, let's call this. This is a linear function, right? It's parameterized by a tensor, which is just a matrix. And a matrix is also a tensor. And it outputs a scalar. Let's say f of x is in reals or whatever. So filter is nothing but same as what you've already seen. But what's different? Okay. So here's an example. Here I've shown a filter which is parameterized by tensor, and so tensor has 3 dimensions, right? So I'm saying, okay, let's say that tensor has dimension 3 cross 3 cross 3. Okay. Which means that I'm using 3 pixels, but which means that the width of the tensor is 3, width of the height of the tensor is 3, and 3 is what is and the third dimension is called the filter depth. And here, this filter, I'm going to map it to the color channels later. But let's just say this is a tensor and it has 3 coordinates, right? 3 dimension values. So what are we going to do with respect to tensor operations is as follows. We have a tensor, right? Which again, just look at it as a box. And filter is also somehow parameterized by a box, right? Maybe it's a small, 3 cross 3 cross 3 box, right? This filter is going to be slid on top of this box. Okay, so maybe I'm going to draw this box here, and maybe at some other point of time it's over here. Okay. So this filter is going to be passed on top of this input tensor. Okay. So here I'm saying that it's slid across the width and the height, which means it's just the surface aspect, right? And the output, when I say slid across the input tensor, let's say I've put this filter or this box on top of the input tensor. When I put it on top of it, it just means that I'm just computing the output of the filter. So I just said I just said f is a, sorry, the filter is a linear function, right? So just think of this part as the input, this part is the parameters of the filter. I'm just multiplying. It's just, since it's a linear operation, you can kind of look at it as a matrix vector product or something like that, and the output is going to be one number. Okay. So we'll actually see what do I mean by that. Here's a picture or diagram where the filter is being illustrated as the orange thing, which is being slid on top of this green input. Okay. So for simplicity, we are just assuming that, let's say the input is a tensor, which is a degenerate tensor. In the sense, there is no depth. Let's say depth is just 1. We'll capture the depth later. So let's say it's just a matrix, basically. Okay. And let's say even the filter is a matrix. So instead of 3, let's say I make it 1. The depth dimension. Okay. So what do I mean by sliding the filter on top of sliding the filter, which is just a matrix on top of another matrix, is just multiply this matrix with that matrix element wise, okay, in that region, and just output that number. So that's what we are doing here. Okay. So the output dimension, output is also a tensor, but it's a degenerate tensor. It's also a matrix because my input is a matrix, my input is a matrix, my filter is a matrix, output is also a matrix. It's of dimension 3 cross 3 cross 1. Okay. The input is of size 5 cross 5 cross 1. Filter is of size 3 cross 3 cross 1. Okay. What if the input was, let's say, 7 cross 7 cross 1? What would be the output size? Same filter. Yeah, 5 cross 5. Right? So you can kind of understand what's happening, at least graphically, right? This is the filter, this is the input, and this is the output. So I've defined a filter which is parameterized by tensor, and given an input tensor, I can just slide the filter, at least for this degenerate case where there is no depth, I can slide the filter through the input and get an output, which is also a tensor. Okay. Now, what I want you to imagine is that, let's say there was a depth. Okay. There was a depth for both the filter and the input. Okay. Let's say instead of one matrix, it was a stack of 2 matrices. Okay. Then what I'm going to do is get as an intermediate result 2 matrices, right? Like you can just think of me sliding the, since you can think of, so let's say this is 2. And in our example, this is 5 cross 5, and this is 3 cross 3 cross, sorry. So let's say there was a depth. Okay. Instead of one matrix, there are 2 matrices. Then what I'm going to do is I'm going to take the first matrix of my filter, right, and do the same operation. I'll get that intermediate box that you're seeing there, that matrix. I'll take the second matrix and do the same operation with the second matrix on the input side. I'll again get the same box. Okay, right? It's just two operations that I'm doing, right? Then what I'm going to do is add the 2 matrices. So this is the 3 cross 3 matrix, and there's another 3 cross 3 matrix. I'm gonna add entry wise. Okay. And I still want to get a 2-dimensional matrix. Sorry, yeah. I just want to get a matrix rather than a tensor. So what I'm trying to say is the difference between what is being illustrated here, which is just a matrix, and what I'm trying to say is that if you go to a tensor level, that is, if you add depth, I still want to get a matrix of the output. And how am I going to get a matrix of the output? I'm going to take the first phase, which is just going to be a matrix of the filter, slide it over the first phase, which is going to be a matrix of the input, get a matrix, right? I'm going to take the second phase of the filter, which is matrix, take the second phase of the input, which is a matrix, again do this operation, again get a matrix. Now I'm going to just add the matrices element wise to get the output, which is 3 cross 3 cross 1. Like, even if there is depth here, I'm saying that for this filter at least I want a matrix at the output, which is a tensor which is degenerate, right? Filter depth, yes. Yeah, filter depth should be the same as input depth. No, I want it to be the same as input. And we'll see that that's see here when I'm presenting CNNs, it's all design choice, right? We are deciding, what should be a filter, what should be called a filter, how much should be the depth on each side. So we're going to define that a filter should have the same depth as the input. Okay. Yeah.
So, you said that for each phase you have a different filter.
Each phase, yeah.
Why don't have the same?
No, it's the same filter. So filter is defined by tensor. It has multiple phases. Since it's a 3-dimensional array, you can think of it as a stack of matrices. That's all. It's the same filter. Filters first matrix, filters second matrix, filters third matrix, and so on.
And also,
Yeah, they can be different. They can be the same. I mean, I'm not imposing any constraint. It's just a 3D volume rather than a matrix. Is what I think. Here you are seeing an example of how a filter operates in terms of getting an output, right? I'm saying even if you add the depth, the output is still the same. It's going to be a matrix. Okay? And that's just written in words here. So things to notice is that filters are small. So in the example also, example input itself was small, but filters are going to be typically small. So in the example you saw 3 cross 3 filter, right? And they need to have the same filter depth. It's called the filter depth as the input tensor, right? So if the input is x times y times z, for example, in the CFAR10 input can be 32 cross 3. If you're really working at the input layer, in the sense the first layer is actually a convolution layer, then its input is going to be this tensor, right? If your first layer in the CNN is a convolution layer, then it's going to get the actual raw input, and the raw input is a tensor, which is of this size. Let's say my filter is actually now, my filter has to be 3 cross 3 cross. It has to be 3 because the last dimension has to match, right? The output will still be something which is going to be still a matrix. Okay. Now that something depends on how the 3 cross 3 thing is being slid across the input, right? In this example, it was being started on the top left and then gradually slid, but it was hitting a boundary. So there are some issues there, but we'll get to that. So what I want to recognize first is that, okay, I'll still get a 2D map. It's called a 2D activation map because once I operate the filter, as in move the filter on top of the input tensor, and get a 2D, intermediate, get a matrix or a 2-dimensional array, I'm going to apply my nonlinearity. So that's why it's the activation map, because I'm going to apply nonlinearity element wise. So max of 0, that entry, max of 0, the second entry, max of 0, that entry. So that's why it's called a 2D activation map. So a single filter with the input image resulted in an activation map, which is just a matrix, one matrix. It doesn't matter how deep the input is. It may not be 3, it can be 10. But ultimately, a single filter will still result in a matrix. Okay. The dimensionalities of matrix depend on, of course, how I'm sliding on top of the input, right? So, what are the parameters of the filter? The parameters of the filter are just the entries of that tensor, okay? And we're going to learn those entries to detect certain visual features. So, we're going to learn those entries anyway. I mean, if it's going to be part of a layer, it's going to be part of a layer. So we'll anyway learn the parameters of this filter such that our end classes still match the ground truth in the training data. Okay. This is just a precursor to what's going to come next. Is that these filters will somehow kind of detect some low-level vision things like edges, like colors, and so on. It's just a precursor. We'll map it back to what actually happens later. Okay. That's all. So before we look at these patterns, which I'm trying to now give a vision-based intuition, let's not get there first. Let's look at the neurons themselves. How are they connected? I just brought in a new object, a filter, which is parameterized by a tensor. But how are they related to neurons? I said convolutional layer, this blob, has neurons in there, right? So how are the neurons related to the filter? Right? I'm gonna answer that question in the next few slides. In a sense, how are the neurons connected, how are they arranged inside the convolutional layer block, and how do we get this reduction in parameters? And this is going to be the key thing. Okay, so let's keep aside our filter notion for now. We'll get back to it in just one slide. But let's say if I had a neuron, what I'm going to do is so let's say my input was a 32 cross 3 dimensional raw image, pixels, right? In the CIFAR10 data set, that's what it was. I'm gonna pick a neuron. There's a convolutional layer. I don't know how it's made up of right now. I know there is a notion of filters, but I'll map it. I'll talk about it later. There's a neuron here. You know that in a fully connected network, this neuron would have connected to every input coordinate, right? Whether it doesn't matter whether it looks like a tensor or not, whether it looks like a volume or not, doesn't matter. Every coordinate here, if you flatten it, vectorize it. Once you vectorize it, it's clear that this is connected to everything, right? So in this case, we're only going to connect it to a small spatial region. Okay. So if this is an image, I'm only going to look at, let's say, the first conveniently 3 cross 3 region, let's say. It can be any small region. And so this is called the receptive field of that neuron. Okay. And this neuron is also, so I only constrain the neuron to connect to only a few of the inputs of the input, right? A few of the coordinates of the input. But I'm allowing the neuron to connect to all the depth coordinates within this confine. So the confine is only in terms of space, right? If the input is actually the image, it has 3 channels, the red, blue, and green channels, then I'm going to connect that neuron to all the RBG, all the 3 matrices coordinates, but only restricted to that region, which is the spatial extent of that neuron called the receptive field. Okay. So pictorially, how does it look like? So if the tensor is 32 cross 32 cross 3, and there is some neuron inside my convolutional layer, because I said that's the first layer. Okay, there's definitely going to be a bunch of neurons in there, and so one neuron. This neuron is restricted spatially to be only connected to all the coordinates of the input tensor of this region only. Okay, and it's connected to all the inputs in terms of the depth, right? In the sense, in this region, it's connected to all the coordinates which are inside in terms of the depth dimension, right? This connection will have weights, and those weights are precisely characterized by the filter. That's the relation to the filter object and a neuron. First connection.
These weights are also randomly.
Whether the weights are randomly initialized or not, we'll get to that later. there are weights. It's a network, right? If it's a network, it has parameters. So those are the weights. But how they are initialized, what numerical value they take, we'll decide it later.
Can you connect the output which you have gotten from the filter and the tensor? There's an output created from the filter and the tensor, right? Can you visually show where that output 3 cross 3 cross 1 is there? That is the
Yes, we will see that in the next slide. But okay, which is this? The output is basically this green box you're looking at.
it's a one dimension or one depth.
Yeah, it's one depth. Yes, this matrix is basically this slice. Okay. But the first connection is that there is a neuron which is only connected to a small region, which means that I'm somehow trying to map the filter's parameters, which is the tensor, to the parameters or the weights which kind of determine that neuron. Okay. And I'm gonna, there will be other neurons which will be connected to potentially different, regions of the space and so on. So I'm not talking about other neurons right now. Let's pick one neuron, and I know that neuron is only connected locally, in the sense of it's not connected to the whole input tensor, whether it's the image or whether it's some hidden layer, it doesn't matter. But it's only connected to a small part. Okay. So if this neuron is only connected to a small part, then clearly I'm reducing the number of parameters, right? In particular, if it's 3 cross 3 cross 3, then there are 27 plus 1 bias parameter for that neuron.
So if you, let's say you have a convolution layer depth of 3, right?
Depth of 3, yeah, okay.
So can each neuron be mapped to one channel of image?
This, we haven't yet talked about the depth of the convolution layer yet.
So instead of having, so each neuron embodies.
For example, here the depth is 5, right?
Yes, so instead if the depth was 3,
Okay.
could we process a 3 by 3 by 1 part of the image? Let's say only the red slice.
Okay. Only one slice of one matrix in this 3 matrices, yeah.
In one neuron, the second matrix in the second neuron.
You could do that, but that is also a different design choice, but that's not what's done in CNNs. Yeah.
Is the filter defined by us?
Yes, the filter's parameters are going to be learned, right? I just mentioned that, right? The filter parameters will be learned such that, okay, I just gave some kind of a vision-based interpretation, but ultimately they'll be learned such that classification is good, right? You have to set the parameters. It's their parameters, so you have to kind of change those parameters such that the classification is good. That's always the meta goal, right? So now let's talk about the notion of depth in the convolution layer. Let's say I stack 5 neurons here, okay, in terms of the depth coordinate or the depth dimension, okay. We know that this neuron was looking at this part of the image or the input tensor, okay. It need not be image if it's somewhere down the line in the deep network. But so what are these other neurons doing? If I stack them in the same depth axis, that means that they're all looking at the same part of the input tensor, okay. That's all. I'm just conventioning. So this is just a convention that I'm imposing, that if I put a neuron on top of this neuron in terms of the depth dimensions, then all these neurons are looking at the same part or same region of the input. When I say looking, it just means that this neuron's connections also go to this guy. There will be probably other weights associated with it, right? So here, in this case, this neuron belongs to some filter F1. Then maybe this neuron belongs to another filter F2. This belongs to another filter F3. This belongs to another filter F4, and so on. Okay. So that's why I was trying to kind of get at the idea that it doesn't matter what the depth. So the filter's depth needs to be the same as the input tensor's depth. Okay. But the filter's output is always going to be a 2D matrix, and that matrix is going to be that matrix. We haven't fully established the connection yet, but this matrix is that matrix. And so, if you want to get another matrix, you better use a different filter. Okay. Yeah.
Can each filter have different dimensions?
Yeah, I mean you can have a 3 cross 3. I mean the input, the depth dimension of the filter should be the same as the input, but these dimensions can be different. Yes. But in the vanilla version, we're gonna just use the same size filters. Okay. Just the numbers are gonna change, but the dimensions don't change. But you can also change the dimensions if you want.
But then if in each, like, across the depth of the
If you change this, then the output matrices may change its dimension. That's the.
But this means you thought that each neuron is looking at the same area.
This neuron is looking at this area. This neuron is also looking at the same area, but it is determined by different filter, and therefore different numbers, different weights, right? Yeah.
But that the filter dimension has to be same. Otherwise,
Oh, the filter dimension has to be same because of a different region. This matrix size is determined by the filter dimension and input dimension, right? If instead of 3 cross 3, I use 4 cross 4 cross, let's say 3, then the output matrix will not be the same size. I'm stacking matrices, right? These are just independent slices, right? Which are the 2D activations. They are unrelated to each other, except they are all related to each filter. Okay. If the filter dimensions are different, which is if it's 3 cross 3 versus 4 cross 4, then those output matrices sizes will be different. Like here, instead of 3 cross 3 for this input 5 cross, like we had the example, right? 5 cross 1 was the example, right? And I had a filter 3 cross 3 cross 1. Let's say I had another filter which is 2 cross 2 cross 1. Then you can kind of conceptually see that if I'm going to slide it over a 5 cross 5 matrix, this area, this area, this area, this area. So I get a 4 cross 4 2D activation map, which is going to be different from the 3 cross 3 activation map, which the other filter was given. So they can't be stacked. I mean, they can be stacked, but they are going to be different dimensions. So.
Stacking in this addition, how can we add?
No, there is no addition happening. These are just stack of matrices. So just a tensor. The addition is happening because of if there was a depth on the input side, because filter also has a depth. I'm just when I say slide the filter on top of the input, I'm just sliding it layer wise in the sense. Okay, the first matrix of the filter is sliding over the first matrix of the input. The second matrix of the filter is sliding over the second matrix of the input. Those matrices I'm adding up, which was the intermediate part, to get a single activation, which is that green thing, right? For a single filter, I just need to get a 2D activation map, and that's that matrix. Okay. Beyond that, there is no addition happening here.
For different neuron, no addition.
No. The neuron operation is the same, right? If it's whether it's connected to the full region of the input or a small region of the input, the neuron's operation is still the same. It just has a bunch of weights. It's connected to a bunch of inputs. Every weight is multiplied to every input coordinate, sum them up, add a bias, and then pass it through nonlinearity. That's the neuron's operation.
we have two filters and so we have to
Yeah, two matrices. Instead of, let's say, green, there will be a green and, let's say, another blue.
won't we add both?
No, we are not. That's the key thing.
The 5 neurons that you've shown here.
Yeah.
They are the only neurons in the convolution layer, right?
Right now, yes.
So those are the ones that will be convolved.
Actually, that's the connection. When I'm saying I'm moving the filter from one spatial region to another, when I'm sliding the filter, I'm moving I'm moving from one spatial region to the other. It's basically trying to say there's going to be another neuron in this green layer or green box, which is looking at a different spatial region. Okay, but has the same weights because it's the same filter. Same filter is operating at the top left part of the image. Maybe there's a neuron over here, which is capturing that at the top left, and that's capturing one number on its 2D activation map, right? When you slide it slightly towards the right, there's another neuron which is essentially like looking at that spatial region and outputting one number. It's going to be the number which is in the second coordinate.
And all those filters are the same with the same filter.
Let's focus on one filter first. Let's not get confused with multiple filters because multiple filters are not doing anything, right? If I think of another filter, it's just adding one more matrix at the output side. That's it. Otherwise, whether there are 2 filters or 10 filters, 100 filters, doesn't matter. Think of what one filter is doing right now. Right? If you had 5 filters, then there would be 5 such matrices, and therefore that's what's illustrated here.
So the neuron would be looking at the some part of the spatial, the current spatial neuron.
Which neuron?
The adjacent neuron will
Yeah, adjacent neuron will be looking at some part of the current spatial region and maybe some new part. Right? We were looking at it from the 2D perspective, like a top view, when the filter was being slid. But it's the same thing as saying, same thing from a 3D perspective as well.
And the depth of the convolution layer can be anything.
Depth can be anything in the sense that if I choose 100 filters, then the depth will be 100. Because each filter is outputting a single matrix. Output is a 3D array. So it's a bunch of matrices. So how many matrices do I want? If I have 100 filters, I'll have 100 matrices because they're all, and I will stack them up and they'll get me the 3D tensor.
So it's like if say filter is 5 cross 5 cross 2.
Yeah.
Sorry, the input is 5 cross 5 cross 2. The filter
Yeah.
will be 3 cross 3 cross 2.
No, that's up to you. You design. Input is not defined by you, right? You can, yeah. The only constraint is the filter third coordinate should be the same as the third coordinate of the input. Yeah.
Does that mean not 2 filters because it's 2 depths?
No, it's just one filter. Filter can have depth. Filter is determined by a tensor. See, filter depth is not the same as the layer depth. Okay. Yeah, filter depth is not the same as layer depth. Did I not mention that somewhere? Okay, we'll get to that if we have not. Yeah.
So in this particular example, you have 3 filters or 5 filters.
No, I'm just trying to show one filter, right?
So is it
Yeah, this has five filters, let's say. This is just a picture, right? I mean, it's not clear. It may have more, right? Because there is some portion here where there's no neuron.
why I'm asking is because you have read 3 layer filters. So is it not necessary that there should be 3 filters to add it from this one?
Once again, guys, there's no point murmuring if you don't understand this concept because this is going to be the workhorse for most of your assignments and project. Okay, so what's your question?
Is it not necessary that we need to have 3 filters here because we have to compress in one layer?
Let's focus on this green region. That's determined by just one filter. If there was one more filter, that would be another slice of this block.
But we have 3, the depth is 3 per first one.
This depth is just determines the depth of the filter itself. Filter is parameterized by tensor, right? Which is just think of it as a smaller scale size input. It's the same dimension as the input, but the space and height are reduced. Yeah. Yeah. Filter's input is the same. Filter's depth is the same as input depth. This depth is the layer's depth, which is something else. Yeah.
How do you decide how many filters to use?
Design choice. We'll see that how we decide later.
For a particular layer depth, is the filter constant?
Yeah, for a particular slice, it's the same filter, right? I'm just sliding the filter all over the place, so it's the same numbers.
So, aren't you sort of making the filter is not going through to the edges a lot, right? It's traveling to the center.
No, I mean whether it's traveling over the image, whether it's
I mean, if you see the first row, first element.
yes,
it goes
there is
one.
an issue. There is an issue. We'll address that in a few slides. Any key questions here? Yeah.
You mentioned something about exponential size.
Yeah. So this picture is just trying to tie it back to the convolution layers tensor, right? But the additions are happening at the level of at this level. So take the first. Let's say the filter is determined by these red, the red coordinates like 1 0 1 0 1 0 1 0 1, right? So that's the first matrix in the filter. Filter is parameterized by tensor. The tensor is 3 cross 3 cross something. Let's say 2. And the first matrix is the matrix which is these red numbers. Okay, that's just being passed. That's just being slid around the input tensor. Input tensor is first matrix. Okay, and the additions are just that entry times that entry, 1 times 1 plus 1 times 1. Let's say that 4 is just 1 times 1 plus 1 times 1 plus a couple of other this one and this one. So this one, these 4 entries determine that 4 number. So you can see that. Okay, in your slides maybe you can see that because it's static. Actually, I have a reference here, so I don't know if I have time. Um, So what does the filter do? I mean, this is still in the it's ignoring the depth, but let's just focus on because depth is just, as I said, whether there was a depth of 2 or depth of 100 for the filter itself, the intermediate matrices would be just added together element wise, right? This is what I was maybe you're confusing here. So if the filter has a depth 2, let's say there were 2 such animations there, it would generate 2 matrices. I would call them intermediate outputs and just add them element wise, squish them into one matrix at the end of the day. For one filter, there should be just one matrix. Okay. But what does the filter do? So here, so this is the image of somebody in grayscale. So there is no depth. Okay, and these are the numbers here, but there is no point looking at the numbers. So this is a 3x3 filter. Okay. In the sense, 3x3x1. It's a degenerate filter. It's just one matrix. Okay, and the filter's entries are predetermined. This filter is called sharpen filter, but let's say the entries of the filter are fixed, then what does this filter do? You can kind of slide around on this image, okay, from here, what's happening, you can see, right? It's basically the filters entries are these entries here, 0 1 0, minus 1 5 1, 0 minus 1 0. And these are the pixel entries of this particular matrix. In this case, is the image, so you can actually see this grayscale image, right? So it's computing one number. That 3 is going over to that. And that's why it's black. Okay. If you let's say it was here, the 270 is going over there. It's white. So 270 is clipped off to, let's say, 255, and so it's white. But anyway, so this is what the filter is doing. If it's going over this matrix, it's producing an output matrix. In this case, it's producing it's producing output matrix which is the same size as the input matrix, because you can see that the filter is kind of overflowing by one, right? But let's say if it was not overflowing, then you would have one less here, one less there, right? And that's why we had, if it was 5 cross 5, we had one less on each side, actually on all sides. So that's why we had 3 cross 3, right? Any confusions? And so this filter apparently is supposed to sharpen the image. You can see it's actually, you can call this a sharpened image. So let's say, what is the other? Let's say, I don't know, outline. I don't know what this is. So outline is this filter which has minus 1s on the top row, minus 1 8, minus 1 in the second row, and minus 1s on the third row. So it's really if you multiply this filter with, if you slide this over the image, you get this as the output. And I guess it's called the outline filter because it's highlighting just maybe the edges or something like that. But this was ancient image processing where they actually named the filters and they were passing it over to get some edges and so on. In the CNNs, the filter has parameters, but we'll learn the parameters by our backdrop, by trying to minimize our difference between our predicted scores and the ground truths. Okay, so there are no names for our filters. Filters is just it's parameterized by tensor. Tensor's entries are not known. We learn them eventually. Okay.
In this case, at the edges when there are no rows and columns, so it will always generate black in this case.
Yeah, it's okay. This one is not. Yeah, this one's. That's why you have blacks here. Yeah, this one. Maybe the other one was doing something else.
But in the case of CNN, then what will happen in the filter falls short of?
Yeah, if That's what the output size got reduced, right? If it was 5 cross 5, it got reduced to 3 cross 3.
No, but in this case, there was a perfect multiple something we can.
Yeah, we need to have filters which are perfect multiples in your language, right? So once you fix this size, once input size is already fixed, then you know what the output size should be. If they are not integers, then you'll have to do something. If they are not integers, I'm not going to go down that thought. Okay. Let's get back. Okay. This we already saw. This is the image. Okay. So back to layer point of view. The size of the output tensor depends on 3 numbers. Okay. The layer depth. Okay. The depth of the layer, and this corresponds to the number of filters. Clearly, right? I mean, I said each matrix is determined by one filter. If I pick 100 filters, then the depth is 100. Okay. And stride, size of the output tensor. So we just accounted for depth. What about the width and the height? Okay. The stride of the filter, which means how am I sliding this filter on top of the input tensor? Okay. If I'm sliding it too fast, in the sense of for example, so we'll look at the example. So if I'm sliding it slowly, as in I have a lot of overlapping regions as I slide, then the stride is going to be low. Stride number is just a parameter; it's going to be low. If I kind of have pretty much no overlapping regions, then the stride is going to be high. So we're going to see in the next slide an example. And zero padding is precisely the thing that you're talking about, where I'll add zeros on the input tensor so that I can hit the boundaries appropriately. If it was 3 cross 3, as I said, you were saying something about me being restricted on the top left, right? So if I add zeros for a 3 cross 3, it's fine because I can have my center of my 3 cross 3 matrix to be at the top left coordinate as well, which was not happening before. So it's just some engineering tricks. Okay. So what do I mean by stride and zero padding? In this example, stride is going to be 1 because I'm just shifting by 1. Okay. If I had shifted by 5, then stride would be 5. But if I could shift by 5, I can't shift by 5 here. Zero padding is none. But if I had added zero paddings, then what would have happened? What would be the output size? Same as the? Yeah. Yeah. So output size will be 5 cross 5. Okay. Zero padding is just to if you want to, let's say, maintain the output size. Okay, and I'm looking at 3 cross 3 filters. Then if I add a pad of one row of zeros on both sides and one column of zeros on this side, one column of zeros on that side, then my output matrix size would be the same as the width and height of my input tensor. No particular kind. You can add it if you want to, and that's convention. As he was saying that if you don't do it, then it's a bit of a lopsided computation that you're doing with respect to your input, right?
So one zero padding also it should be lopsided because if you're going over the first row of person only once.
Yeah.
Like one time lesser than the other.
Yeah, it's still lopsided, but zero padding is just to maintain the dimensionality of the output tensor. Let's say I don't want to change the dimension of my output tensor. I want to keep it the same. Then you can add zero padding. Okay. So now comes the important part, which is the reduction in the number of parameters. The whole point of studying CNNs is supposed to have lesser parameters than the feed-forward neural network of the same, let's say same number of layers and so on, right? So the key assumption is if a filter is useful in one region, then it should also be useful for another region. In the sense that, let's say a filter is detecting sharpness, or you saw an edge detector, let's say. You saw the image example on the HTML page, right? Then it should also be, it's the same filter should also apply for detecting edges elsewhere, okay? And that's the concept of sliding. So if this is called a depth slice, and if I slide over this input, the same filter is being reused elsewhere, because if this filter is detecting, let's say, sharp contrast in its input tensor, let's say it's actually the image, then it's detecting an edge, then the same filter elsewhere will also detect an edge. Okay, it's really so that's the key assumption. So this assumption is only useful for vision, for unstructured data which are images. Okay, so for images, because of this assumption, we are gonna reduce parameters, and you can already see that how we are reducing parameters. All neurons in each depth slice, which is that matrix, 2D activation matrix, use the same weights and bias parameters. So we just kind of captured, we just had a reduction in the number of parameters by width cross height, right? All neurons, let's say there's another neuron here, some other circle, it will have the same parameters, because that is also captured by the same filters, tensor coordinates or tensor values, right? So all the neurons in this depth slice have the same parameters. And so the number of parameters is reduced. For example, let's say the number of filters is m, okay, because that's inconsequential right now. Then this layer has 3 times 3 times 3 plus 1 parameters. In this case, because I kind of in my illustration, it was 32 cross 32 cross 3 as the input tensor. So, and I said my filter is going to be 3 cross 3 cross 3, because the last one is fixed. I'm going to have one more number, which is going to be the bias. Okay, whatever the filter produces, I'm going to just add some constant and then pass it through the neuron for the nonlinearity part. Okay, and so the number of parameters in this layer is just this much. Okay. So parameters have reduced, but I'll have to do something about the gradients, and this we're gonna kind of account for later as well. If I'm thinking of parameters in the feed-forward network, I said if I'm at a particular candidate parameter, let's say W0, B0, I need to move to W1, B1, right, by gradient descent, by backdrop, and so on. Here, since the parameters are shared across multiple neurons, I'll have to do something, and that basically you have to add the gradients that you get. When you look at the local gradient of each neuron, you kind of add those gradients up. Okay, we'll get to that, but let's see. So AlexNet, which is the net we are talking about in the when I started the CNN slide, I said the large scale visual recognition challenge, the 2012 performance, which had a reduction of 10% absolute performance in the classification error. That's called the AlexNet. So AlexNet's first layer has this size filters. Okay, 11 times 11 times 3. So ImageNet also has images, and so those images also have three color channels. So the input size is whatever. We are not gonna discuss that, but it's 200 cross 224 cross 224 cross 3. Okay, it's inconsequential here. The filter size is this, and a first layer has 96 filters. So that tensor that you saw has 96 matrix slices, right? And if you actually look at just the filter is just 11 cross 11 cross 3, right? So this is just a 11 cross 11 cross 3 being represented as image, and that's why you can see color, right? If you did not have the 3 part, then you would just see a matrix, and so a grayscale thing. So these are the filters that have been kind of learned by this particular net, which does really good classification. And it kind of captures the intuition that if capturing an edge is important for the classification task, then it is important everywhere in that image. Okay. So here you can see certain types of edge detectors, some maybe color contrast detectors, some check pattern detectors, all sorts of detectors, or all sorts of filter tensors. And in the sense, these tensors are useful for getting good classification accuracy. We are just visualizing the tensors, how they look like. Okay. And we actually saw that in that HTML page that like a tensor like this, which is essentially a matrix, is detecting edges, for example, right? A sharpen or something else that we saw will also have entries similar to this, although this is a different size filter. Okay. Yeah.
Is each of these filters looking at the same area of the image?
No. Filter is independent of the area of the image. Right? Filter is slid across the whole image. The filter's depth should be the same as the input. I mean, we are only looking at the first layer. So the first layer's input is going to be an image, right? But it can be nth convolutional layer, so its input can be some other hidden layers tensor. But anyway, that apart, this filter is slid across the whole image. Okay, just detects if so. Basically, what does the filter do? Since it's multiplying element wise, since it's slid in the sense of element wise multiplication, if the pattern looks like this, then that's going to get amplified. If the pattern doesn't look like that, that doesn't get amplified. So the filter is essentially like detecting some pattern which looks like this, right? But it's slid all over the image, and then you'll get an output, which is whatever is image dimension. I mean, it depends on the computation that you do. I mean, the filter size and the input image size.
So are we saying that the image has some
If the image has something like this in some portion,
triggered image?
then that neuron will kind of have a high activation. I mean, will have an activation. I mean, a pre-activation, which is before passing through the nonlinearity, will be high because if they have exactly something like this. Yeah. So let's look at again a summary example. Input tensor is, let's say, 90 cross 90 cross 10. So it's not the input, it's not image anymore. It's some other hidden layers output. And say we have 5 filters, okay? And each filter is 3 cross 3 cross. The last part is fixed because it has to be the input size. Stride is, let's say, 1, and zero padding is 1. Okay. Then the output tensor is going to be 90 times 90 times 5. Is that obvious, clear, or not clear? Huh? Who's not clear about this? You're not clear about this? You're fine. So which line? Let's say input tensor, is just definition. There are 5 filters. Of filters are also specified with tensors, and I'm saying it's 3 cross 3 cross 10 dimensional tensor, specifying each filter, right? Stride is 1 and zero padding is 1. Is what is confusing you, or is fine? The output tensor is 90 times 90 times 5. That 5. This 5 is the same as, because I have 5 filters, the depth is fixed as 5. And the other two coordinates are 90 because I chose stride as 1 and zero padding as 1. If the zero padding was 0, what would have happened? 88. Oh, you reduce 1 on each side, right?
88.
Yeah. Yeah, it's going to be 88. And we can calculate similar things. So, and so this is just manual, that's just not very critical. But the critical part is the number of parameters. So for this layer, the number of parameters is 5 times that, which is here, it's 455. Okay. But contrast this with a fully connected network. The number of inputs is 90 times 90 times 10, right? So if you vectorize the input, it's 81,000 dimensional. Number of hidden layer neurons is number of hidden layer neurons is supposed to be half of that, sorry. And then the number of parameters is just the product of those two, which is going to be at least this. If you kind of set biases to be 0, if you put biases, it's going to be greater than that. So let's, that's a reduction in parameters. And why did we achieve that? Because we said, filters, whether they detect edge on this side or that side, they are still detecting edges, and detecting edges probably is a good thing. We are kind of restricting our parameters basically. And the same thing again, another study example. These are the 3 boxes of images. 3 matrices which kind of, let's say, characterize the input. It may not be image, but let's say 7 cross 7 cross 3, and the filter is 3 cross 3 cross 3, then okay, in this example I'm just focusing on the second filter, so let's ignore the first filter. The first filter is going to start looking at the top left and generate one number. The second phase of the filter matrix is going to look at the second phase of the input and generate one number. This one is also going to look at this and generate one number. It's just element wise multiplication. 3 numbers are generated, right? Those 3 numbers plus 0 will go as one number on the 2D activation, right? So same thing happening in terms of animation, but basically the name convolution comes from convolution operation single crossing, which is essentially a matrix product. So this is the element wise product that we are doing is related to convolution. Okay, is this clear? Okay, now we'll take a short break of 3 minutes, let's say. Yeah. So forget about all the depth issue. Depth is ignore the depth. So let's say I have a matrix 7 cross 7. This filter is 3 cross 3 cross 1. I said put this block on this block, so I put it over here. I have numbers, I multiply, and I add a bias. So multiply, I get one number. Oh, sorry, I get this. Multiply, I get one number, and I add a bias. Something else. So I get some one number. So when I say I get one number, why do I get one number? Although, so the 9 numbers are 9 numbers there. Coordinated by the multiplier numbers. And then I'm adding them up. That is getting one answer. Right? That's one, let's say, for this section. So this is here. This now, just exit between minus and these. Okay, doesn't matter. I got this one number, right? Now, when I said multiply this filter with the inputs, that's what neuron also does. Neuron, if you remember you can just vectorize this. Vectorize this x1 to x9. No, that's the key part. One filter is actually equal to multiple neurons in that way. For all neurons, for many neurons, so let's say this neuron number 1, let's say this other neuron number 1. Although it's existing because it's looking at a small region of the input, this one is looking at only this part of the input. This neuron. This neuron is looking at some other part of the input. These are neurons. One Yes. Although, so the nice thing is, although I can have lots of neurons, the number of parameters still the parameters in the filter only. So I could have 10,000 neurons, but the number of parameters is still 9 plus 1, 10. Tensor is three-dimensional or n-dimensional.
It's basically a matrix which is
Three dimensions you can think of it as matrices, a sequence of matrices, collection of matrices stacked in
dimension, it has a height and a weight.
yes,
But
yes,
if you add depth to it,
yeah.
it's a cube sort of a
Yes, yes,
cube.
yeah. I mean that's not the definition. It says that is a three-dimensional tensor, but there could be higher dimensions, but they are hard to visualize. That's what they are. Yeah, it's basically stacking numbers. You have a matrix, another matrix, another matrix, and because it's three-dimensional.
Why does it have to be for tensor? They have three layers of tensor, right? If you just have why did you have it in one?
Yes. Yes, yes, yes. No, because when the filter is acting, it's actually merging the outputs, right? So this is just convention. You can kind of look at CNNs as not tensor based, but just matrices, sequence of matrices based. But then the representation of the two clumsy. Okay, this is going there, that's going there. The tensor is kind of easy. You're just thinking of it as filter sliding over an input tensor. Filter is also a tensor, so you can have depth, but the depth is the same, so those numbers kind of exactly align. And I get output a single number that's like to the neuron, passed from analytic goes up. But now if you kind of put them separately, then you have to account, okay, I'm looking at this matrix and then some other matrix. Yeah. 96 boxes are there, but each box is 11 plus 7 plus 3. Each box, there are 96 filters. Yeah, 96 squares. Each layer is a matrix. Other masks now, because the first layer you have the intuition input was an image, so it has three depth, so the filter has three. But once you get to this box, you have another convolution layer. It's not three, I mean, there are 96 depth. The filter has been 96. See this is. No, it doesn't have. Yeah. Width and height can be modified. 3 cross 3, 5 cross 5, one matrix. What is the best one? So I don't understand what it is. Yes. It has depth of 3. That's why we'll add as an image. No. Irrespective of the depth, the output is always pretty abstract. For a given filter, the output is always a matrix. Yes. Because we have because the input has depth. You can say match the input. Yes. You have different size matrix and what will you do with it? One slice.
Yeah, and then these will be
basically you get 96 slices.
96
matrices.
which is actually the dash of my output.
Yes.
And then what you do with these layers?
You will pass down another condition.
And this will be
That's a tensor. Yeah, that's output for the first layer. But once you get the output, you ignore the first layer, let's say. Now think of this as now my input tensor. I'll have to filter this again. Then my next filters will have to have depth in 96. three indices, but the filter size can be modified. Yeah. And I connect all of them to a single unit. That's why I have a fully connected. So I connect all inputs. As good as saying I don't have data, I'll just vectorize them. Stack all the numbers and just connect it. Each neuron is connected. All inputs. So for me, at the end, that's a Element-wise, basically, taking the x rate, taking out the current rate, multiplying it, summing all those things up, adding a bias, what we are doing. That's what a neuron does.
It's not like a manual basis of the nitrogen. It's like a single
Yeah, vector. Yeah, towards the end. We get to that. That's it then. Okay. Hello. So we are going to now look at the pooling layer. Hello, everybody. Okay, so the pooling layer is vastly more simple. Okay. So the objective of the pooling layer is just to reduce the spatial size of its input. Okay. So the pool layer gets a tensor as an input, and all it is concerned with is trying to reduce the size of its tensor input in the spatial dimensions, which is the width and the height. Okay. And so you might as well think of it as operating independently on each depth slice. So you don't again care about depth. Okay. So pictorially, what's happening? Let's say my input tensor is this times 64. Okay. If I pass it through a pool layer, then pool essentially is supposed to do some downsampling. So let's say it downsamples by 2, then I'll get a tensor which is 112 times 112 times 64. Okay, so the depth is the same. The width and the height of this tensor are getting changed. Okay, as in, like, if you pick a matrix here, you can kind of look at it, because if you look at it, the low entries are dark colored and the high entries are white colored. Okay, it's just a pictorial representation of a matrix. Then if I downsample it, I'm just supposed to kind of retain the rough, coarse patterns in that matrix. Okay. So if you look at a single depth slice, okay, if you just look at the single matrix, let's say the matrix has entries like these, then a specific tag, let's say I add something called, not add, but I'm going to specify what this pool operation does. So let's say it does max pooling, okay, and its size is 2 cross 2, okay. So I have introduced 2 additional attributes to the pool operation. It's max pooling and the filter's size is, okay, it's called 2 cross 2 filters, but you can ignore the filter part, so it's some additional numbers, and size is 2. Then all it's saying is, I'm going to bunch up these 4 numbers, take the max value, output that. I'm going to bunch up these numbers, take the max value, output that. That's it. Okay. This is what is going to be downsampling in the spatial dimension. Is that clear? So why is there a 4 here? Is that clear? Who is not able to understand why there's a 4 there? Okay, the 4 is there because it's the maximum of these 4 numbers, and this 2 cross 2 just means I'm going to look at a 2 cross 2 block. Okay, and stride 2 means I'm not going to overlap, in the sense, let's say I was looking at a 2 cross 2 block, but then I have a stride of 1, then I'll have to look at this 2 cross 2 block, which I'm not doing. So I have non-overlapping things, so that's why I've taken stride of 2. Okay, so because I took stride of 2 and 2 cross 2, in the sense I'm looking at 4 numbers and I'm taking max pooling, I've reduced my dimension from 4 cross 4 matrix to 2 cross 2 matrix. But just a pointer that recent research is showing that one may not need a pooling layer, but the 2012 to 2014 architectures, 2015 architectures, all of them have pooling layers, and that's why we are studying them. Okay. So that's it. That's the pool layer. It's not. There's no neuron in pool layer, so that's why it's easy to describe. Okay. It's just taking the input tensor slice by slice as a matrix by matrix and just shrinking it height wise and width wise. Yeah.
So is the input to the pool layer is the output of convolution?
Yeah.
Whatever that says.
Yeah. But we don't have to be concerned where the input is coming from. I mean, a pool operation is fine itself is just determined by these, right? Whether the input is from a convolution layer, whether it's the image itself. If the input was itself an image, then you are just downsampling the image, right? You are just making it a smaller, instead of 800 cross 600, it's maybe 400 cross 300, right? Yeah.
Can you suggest a few examples of this, like not only max, something else?
Take the average, take the minimum.
I mean, what in general?
Downsampling operations, huh?
What do you use in general purpose, like in practical purpose?
No, this is what is used in the state-of-the-art
In
AlexNet. AlexNet from 2012, the image processing, the image recognition challenge winner. Yeah. I mean, in fact, this is what is used subsequently after a couple of years as well, but I think the most recent ones, there is some research showing that you don't need pooling, as in you don't need a pooling layer, but the most recent research, which has not been battle tested. Yeah.
What will result in a loss of information if you use it like this?
Yes, this objective is to lose information. If you don't do this, why are we willing to lose information? It's not that we are losing information actually. If I have more filters, then I'm just reshaping my tensor. So think of it this way, right? Let's say I had a image which is 224 cross 3. Okay. I pooled it. Pooling is not really changing anything. But the convolution layer will have filters, right? Let's say I chose 6 filters, and I keep the stride to be 1, filter size to 3 cross 3. Then I get a 224 cross 6. I had these many numbers. I just doubled my numbers. If I pool, I get 112 cross 112 cross 6. Okay, maybe I should have done. Let's say 12 filters. Convolution. Okay, I got this, which are a lot of additional numbers, 4 times more numbers. I did this, I lost 4 times more numbers. So the number of numbers here, number of numbers there is the same. So.
Or it will be
Sorry, yeah. This has to be the same. Depth is inconsequential for pooling. So yeah. Is this clear? Is this example clear? Yeah.
So, which layers will the pooling come? You're saying it won't be a neuron.
It doesn't have a neuron. I mean, you can look at it independently, right? Whether it comes before or after some other layer, it doesn't matter. Input is a tensor, output is a tensor. The tensor's depths are going to be the same. So if input tensor's depth is 12, output tensor's depth is 12. If input is of some width and height, I'm going to reduce the width and height somehow. In this case, I'm reducing it by half on each side, on each dimension. That's all. So whether the input tensor comes from a convolution layer or some other layer, it doesn't matter. Maybe it could come from another pooling layer. It doesn't matter. It's a tensor, right? Output of some other operation you need not be concerned with in this myopic view, atomic view. So that's it. That's the 2-slide explanation for the pooling layer. It doesn't have any neurons, so it's easy to explain. It doesn't have pretty much. It has parameters, but once you fix them, for example, I'm going to take the max operation. I'm going to take 2 cross 2 filters, and I'm going to take stride 2. Then, although they are roughly parameters, they are not really the number parameters like weights, so they are not typically changed. Okay, you're not optimizing over them typically. Although, if they are parameters, you can still change them and see whether the classification improves or not. Okay. The third type of layer, which we have already seen, at the beginning, or in the previous lecture, is the fully connected layer. So now that we have described the convolution layer, fully connected layer is just a special case, right? Do you agree or not? Why am I calling it a special case?
All the neurons in mind are connected to all the
Yeah, so there you are not sliding anything. You're just multiplying entry wise. Yes, right? Yeah. So there is no sliding operation. Just one filter.
Filter size.
Huh?
Filter size is the input size.
Filter size is the input size. Yes. Filter size is the input size. Yes. Correct. Filter size is the input size. Then the output is gonna be. Wait. Sorry. No, filter size is not.
It says 1 cross 1.
Yeah. 1 cross 1. Sorry. Yeah. Sorry about that. No. See, if the input is 224 cross 224 cross 3, then all these have to be. So it's like if you look at the neuron point of view, each neuron is supposed to be connected to all the entries of my input matrix, right? So that means filter size is 224 plus 224, right? Yeah, it is correct. Sorry. Okay, you had a confusion then.
Yeah, I think filter size should be 1 cross 1.
No, it's the same. Each neuron. So I only have one slice. I only have one filter. It's not because I have one filter. My output is just
In this case, there should be no filter, right?
What should be the output?
No, that's what we're defining filter because fully connected layer is a special case of convolutional layer, right? Where the receptive field is the whole image. Because the receptive field is the whole
If
image.
filter size is the same as the input layer, shouldn't the output just be 1 cross 1?
Okay, so the okay, sorry.
So filter size
Yeah, filter size is 224 plus 224.
But
No, it's not
output-
one.
If filter size is the same as input, shouldn't be the output be 1?
Yes, for that filter it's one. But I never said there's only one filter.
Okay.
Okay, I probably said it's one filter, but it's not correct. You need to have many filters, right? Do you understand?
Yeah.
Because the hidden layers are not determined by my input at all. I can have 100 hidden layers, I can have 1 hidden layer, I can have 1000 hidden layers, which means all these neurons, think of it as like a layer with one neuron but in different slices. So each slice is dimension 1 cross 1, right? Which means that each slice, there's only one neuron. That neuron has a receptive field or whatever the spatial region, which is the whole image, right? Sorry, is that confusing to other people? Do you need an explanation? Okay, so I said a fully connected layer is a special case of convolutional layer because you remember in the fully connected layer or a fully connected layer in the feed-forward neural network that you saw, like you saw one hidden layer, right? That has neurons. Each neuron is connected to everything in the input, right? It's as good as saying in the 2D view, in the tensor point of view, there is a neuron in this layer, right, which is connected to everything in my input, rather than restricted by space and width. Because it's connected to everything in the input, that means that there has to be those many weights, and that's why the filter size is the same as the input size, right? But that's just one neuron. I can have hundreds of neurons in my, that's my free parameter, right? I can have 100 neurons in my fully connected layer. That means 100 different filters. So those many parameters. So there are very lot of parameters. Yeah.
The number of neurons in this fully connected layer would be equal to the number of neurons, the filter the neurons would be.
Yes. Number of neurons which you can determine. You can have whatever, because number of filters is whatever you determine. Yeah, you're correct. Is there any other confusion? Okay. So let's look at a few other points. So typically, somebody was trying to understand what's the input to the pool layer, what's the input to the convolution layer. Typically, a convolution layer is followed by a pool layer. So convolution layer, I'm including the nonlinearity. Some descriptions, some other courses may sometimes keep the nonlinearity layer a separate layer, but it's just an element-wise operation, so there's no point studying it separately. Yeah.
Sorry, I'm going back to the pool layer.
Yeah.
Then the layer downsamples, but it can capture the general pattern. So are there some functions that will do that will capture the general pattern?
No, it just has to coarsen. Its objective is to coarsen the input.
The
In
thing
the
is like
Yeah.
the image is somewhat capturing the pattern.
I mean, this is just a matrix which is being represented as the image. Yeah, I mean, downsampling always captures the patterns in the.
Functions that are not mentioned. Functions that some function.
No, it's just like an identity matrix. So identity operation will capture every pattern in the input, right? I'm just saying I'm going to coarsen the patterns. So if there was a line of length 4 here, there will be a line of length 2 here. That's all. That's because of my local operation, which was this, right? So in the sense, it's capturing a deterministic pattern. Whatever is the pattern, it's just a coarsen. It's like resizing your image. If you had a 800 cross 600 image, I'm just, it's like go on to paint and resize your image and output it, right? That's what it's doing. Any other question? Yeah.
Does the fully connected layer have depth?
We just when I said it's a special case of convolutional layer, it had depth, right? Which is arbitrary. You can pick. If I want to have 100 neurons in this layer, then the depth would be 100. But you don't have to. Like once you are thinking of a fully connected layer, you might as well think of it as bunch of neurons, which was the traditional view that we saw, in last lecture. So typically, convolution is followed by a pool, and we kind of captured why there is no loss of information as such. Hopefully, the additional filters are capturing information such that there is no loss of information. Closer to the output, you typically have fully connected layers because there is no pattern to exploit as such. The whole point of using a convolutional layer was these filters were either detecting edges, detecting some circles, detecting colors, two colors, and so on that we saw. Those types of things don't happen as you move forward in a neural network. So towards the end, you typically use fully connected layers. And also in the convolutional layer, typically smaller filters are preferred. There is some explanation, but ultimately empirically this works better. So the original AlexNet had 11 cross 11 cross 3 as the filter size for its first convolutional layer, which was getting input as the image itself, right? Later on, I think the later on architectures are just using 3 cross 3 cross 3 filter sizes, for example. And ideally, you want to have input image size be divisible by 2 many times, right? So if the dimension doesn't match, then you have an issue. Like for example, as a pooling is divided by 2 roughly, in terms of width versus height. So if you have lots of pooling operations, then you want to have multiples of 2 as the input image size and so on. And so, for example, this is let's say a CNN architecture may look like this. It will have input, conpol again, and FC, 2 FCs. Doesn't have to be 2 FCs. It can be any. Once you have been given these layers, you can put them in any order. These orders typically make sense empirically. Okay. Quick note on backpropagation. So how do you backpropagate? So you don't have to actually do this by hand in real life, but the computation engine, for example, TensorFlow or TNO or something else, they do automatic differentiation, right? So this backpropagation is just a special case of something called automatic differentiation, which is that once you write this neural network description in Python, let's say in TensorFlow or some other module called Keras, there is an intermediate thing which is made, which if you remember is called the computational graph. Once the computational graph is created, then TensorFlow will take it and it can do the forward propagation, back propagation to compute gradients for you. Okay. I mean, you'll have to define the forward propagation and back propagation a little bit, but the gradients themselves will be automatically available to you. Okay. So back propagation through a conv layer. It so happens because conv layer, you can think of it as filters, which are matrix multiplications. here also it will happen that the propagated gradients also will look like matrices, and so you'll still have matrix products. In fact, you will have a matrix product where one of the matrices is actually a flipped version of the filter itself. Those details are not important. I'm just saying that when you backpropagate through a convolutional layer, you will multiply with some local gradients, right? Those local gradients are just functions of the filter parameters themselves, and specifically it's just some transpose or something like that of the filter. Okay, and backpropagation through a pool layer is essentially like a ReLU. You remember, pool is just taking a max of 4 numbers, let's say, in the previous example. Then you just have to keep the track of the index of the maximum, because it's like a gate, right? So let's say if the maximum was one of these 4 coordinates, let's say. So let's say maximum was A. Then when you're backpropagating, whatever was the, C was the output of some neuron, right? C was the output of some neuron, right? So here the gradient would be 0, and here the gradient would be whatever 1 times the input gradient, whatever that is. Whether it's a vector, matrix, don't worry about it. Okay. And second point that I want to just bring out is that there is some partial robustness to the input size, although the whole CNN architecture can be is specific to the image sizes that you want to look at, right? ImageNet images, at least AlexNet required images to be of this size. So if you had a different size image, you had to kind of massage it into a 224 cross 224 cross 3 image size image. Okay. This image size kind of determines the tensors in the intermediate stages, right? If it was 224 cross 224 cross 3, and I had 10 filters in my convolutional layer, first layer, then I would have 224 cross 224 cross 10 if my filter size was, let's say, 3 cross 3 and stride was 1, right? So, and zero padding was 1 and so on. So, if I've been given these numbers, if all my images in my training data are of the same size, then it kind of determines all the tensors later on that follow, right? Of course, there are other design choices like filter sizes and so on. But what if we have a larger sized image? You can downsample it somehow and make it fit into a 224 cross 224 sized image, or you can also do another thing, which is, as I said, FC fully connected layers are just equivalent to convolutional layers. So you can convert in terms of implementation, kind of look at a fully connected layer as just a convolutional layer, okay? And then you can just slide the original convolutional neural network over the larger image. So now we are sliding the whole network on the image rather than filters on on images, okay? So the whole point is that I'm talking about partial robustness because if I had a larger image in my test set, let's say I've trained my classifier which classifies, let's say, humans versus animals, then let's say it was trained on 224 cross 224 size images. Now I've been given a 800 cross 600 image, on which I need to classify. Then what am I going to do? I can just take my CNN and slide it over my input image, okay? That operation can be done in a single forward pass. In the sense, although I'm talking about sliding, I can basically, given a larger size image, I can compute something on the outside. It won't be a score vector, single, let's say 1 cross 1 cross 1000 score vector that you used to have for the AlexNet, right? I had 1000 categories and this was the image size, so I was getting a single, 1 cross 1 cross 1000 dimensional score vector. But I have a larger size image, so I'll not get a single score vector. Okay, I'll get a bunch of scores. So what I'm saying is pictorially represented here. I'll have a whole CNN itself. So let's forget about the internals of the CNN. Let's say this is a bigger image. Okay, CNN will take a certain size image, and that's represented by, let's say, the face of the CNN. But I have a bigger size image. Then I can just take the CNN, give a partial part of the image, get a score vector. Give another partial part of the image, give a score vector, and so on, right? I'll get a bunch of score vectors. Maybe I'll take the mean of the score vectors and predict that, okay, there is a human in this image, maybe there's an animal in this image, right? But this sliding operation conceptually you can do it by just doing a single forward pass because of the local nature of the filters. Because the filter doesn't care, I mean, it cares about some multiplication factors, but it doesn't care about the actual width and height of the image. Okay, the filter itself. Right? Is that clear or no? Okay, if it's not clear, then you can at least do this naively, right? You can slide your CNN from left to right.
You're basically cutting the image into subsets of 224. That way.
Yes. You can do that and get the same output, but you don't have to actually cut it because CNN architecture allows you to pass this image in one pass. Like there is no sliding operation. In terms of implementation, you don't have to actually slide a CNN in the sense of write a for loop and make the CNN go, slide across the input image. You just have to. You can easily just pass the whole bigger image directly to get a bigger tensor, which will have to average. Yeah.
What are the subjects in between the two parts of the image?
There are two subjects.
No,
Then there will be two scores.
No, there's one subject, but it's right in the middle of where you're partitioning the CNN.
I'm not partitioning the CNN. This is the CNN I built from my training
No,
data.
but you're partitioning the image, right?
No, I am not partitioning it. This again has a stride and all that, right? Because I can have overlapping parts that I can look at and so on.
So it is sliding.
Yeah, it's sliding across, but it's not. The slide can have a stride of 1, which means I'm leaving one pixel, one row, one column at a time and sliding. It's right. I don't have to have a non-overlapping sliding procedure.
So I guess the question is like this: if you're trained a CNN
Yeah.
on a smaller set of images,
Yeah.
and then you want to use the same CNN for a bigger set of image,
Yeah.
you may have to retrain it because the cat will be retrained.
No, you don't have to retrain. I mean, in the sense of if you want to use it, yeah, you may have to retrain it. There are a few things. I mean, if the image is really a high resolution image, you can downsample it, right? But the image, for example, the image, let's say, is not 224 cross 224, it's 800 cross 600, okay? But maybe the cat sizes are the same in both pictures. Then downsampling it may not be, necessary. You can. What I'm saying is, once you have built a CNN, in terms of getting the score vector or a prediction, there's nothing. Although I'm saying you have to slide it this way. Now, in terms of implementation, you don't actually have to slide. In the sense, you can pass the whole image through the CNN because the height and width are kind of not very. They don't break the architecture at all. Like the filter, if it has 2 additional blocks to go, then it'll just go there, right? Think of sliding, right? There's really nothing preventing it from working on larger size height width. Only the fully connected layer has an issue, which I said, you can have a fully connected layer. Now fully connected layer has to be moved, right? But you can think of it as a convolutional layer and it can be moved. This is not critical. I'm just saying that you will in your project or assignment see that image sizes may not be the same. It's not that you have to do this. Do something. You have to do something to get. Let's say if you're using a pre-trained convolutional neural network, then you'll have to use that was pre-trained. Let's say you can download the weights of a particular neural network, right? Let's say AlexNet is available online. You can download it, but it will only work on these size images. Now, if you have 32 cross 32 images, maybe you can upsample them somehow, like enlarge them to get into 224, or let's say you had a bigger image, then you want to somehow shrink it into 224, or you can do this. What I was saying, conceptually sliding, but in terms of implementation, there's probably 1 or 2 tricks that you need to do in TensorFlow, but nothing much. In terms of there's no actual sliding needed, is what I'm saying. Okay, so next we're going to look at visualizing CNN. So again, the common criticism with CNNs is that we are really training a model which has millions of parameters, right? The fully connected model had billions of parameters. We just saw a billion, 3 billion number, right? If every neuron was connected to everything in the input, there was a 3 billion number, which we did not want to do. So we picked CNNs because of parameter reduction as well. We look at 4 attempts to try to understand what's happening in a CNN. And so what we're going to look at activations, which are just outputs of layers. Okay, outputs. Let's say output of the convolutional layer. We're going to look at weights, which are let's say filters filter weights. We're going to look at the images that activate a neuron. Let's say I pick some random neuron in some layer, right? And I want to see which images really kind of make this neuron output a high value versus a low value, because the output of a neuron is just a scalar, so it will be a high value or low value. I can also look at images in an embedded space, in the sense of I get a CNN and I can try to see if the CNN kind of the activations or the weights kind of make images which are similar fall into a low dimensional embedded space. So we'll get to that. So let's see. What's the use of looking at activations? So these are the activations of a particular image. I think in this case it was actually a cat, but you can't see the cat. Here. So if I'm just plotting the activations of the first convolutional layer. Okay. Okay. I just counted. I was just counting. So this convolutional layer has yeah. So it has 36 filters. Okay. 36 filters. So it has 36 layers on the output side. So we're just looking at and the let's say the nonlinearity is value, I think, in this example. So it's just seeing which if you look at one depth slice, which pixels got a high value, which pixels did not get a high value. It's a trained network, in the sense I've already trained this network, some CNN, and now I'm trying to understand how is it working. That's the whole point of this part of the lecture, right? How is it working? So I passed an image of a cat. So I'm just seeing, okay, some neurons are getting active. Sorry. Some coordinates are high, some coordinates are low, right? It's a matrix. So black means low values and high means high values. Sorry, white means high values, right? So when I pass a cat, I'm seeing that, okay, maybe some layer, maybe this is the fourth layer, I can see some edges. Maybe it's an edge detecting filter or something like that. I can see some edges in the first convolution layer. In the fifth convolution layer, remember that the size kind of shrinks of the input tensor. Right? Because I increased the number of filters. Now the depth is 36, right? So from 3 I went to 36. So I hope I shrunk the size of the width and height. So on the fifth convolution layer, you're seeing that, okay, this has so many filters. Okay, let's focus on one filter. This filter has some high value in this region. Okay. So that's a visualization. Whether this visualization is helpful, that's for you to decide. But one thing is you can definitely debug dead filters. For example, if you're using ReLU, we mentioned that ReLU is a nonlinearity, right? And so if you somehow set up the weights such that the weights times the input never crosses 0, then it's always going to output 0. Then maybe you can look at a region and pass all your training data and see if that region never has any white patches, then it means that it's a dead filter. It's not really detecting anything, right? So that's the thing that you can visualize with respect to input. With respect to activations. I feel the first layer's activations are worthwhile to kind of plot, but these you can't really make out. So let's visualize weights. Okay, let's go one by one. I said 4 things we can try to visualize. Let's go visualize the second thing. These are actually the filters. We are just visualizing the filter weights of the AlexNet. Okay, AlexNet has 96 filters, if you remember, right, in the first convolutional layer. So we're just visualizing the weights of the filters. So remember the filters were themselves 11 cross 11 cross 3. If you remember that slide. So each image here is 11 cross 11 pixel image. And the 3 is basically giving the color part. Okay, so you can see that these weights or these filters are kind of representing the patterns that they're gonna highly correlate with. So if they find something like this in some part of the image, they're gonna be, they're gonna output a value which, when passed through the nonlinearity, will hopefully be high. Okay, and if there's a part of the image which has this green color in circular fashion, then that coordinate will be high. Okay, in the activation part. And the same thing on second convolutional layer. There's so many filters. I don't know how many filters there are, but it's really kind of hard to kind of eyeball them. But one thing you can actually eyeball is to when you're training is that these filters have to be somewhat smooth. Okay. If there is some random noisy kind of structure, then you're probably not training correctly, something like that. So visualizing activations and weights are okay. At the beginning, maybe at the first convolutional layer, they make some sense. So let's visualize a third thing, which is let's pick a neuron, in some layer, let's say some last, but let's say third layer, some layer, and we're going to look at images that activate that neuron. Okay, I have this my training data. I can pass each of my image through the network and see which image gives the highest activation value. Right? I picked a neuron. Neuron's output is a scalar. Which image among my set of images is going to give the highest scalar value? Right? And so some guys did that, and the attempt was, of course, to understand what that neuron in that layer was tracking. Typically, so here they are actually showing which receptive field. So these are neurons which are higher up in the convolutional network, and that's why they're kind of capturing a huge portion of the input. That's why let's focus on this, right? So the white box is showing how much area that neuron is seeing. So if you remember, the first convolutional layer, if it's a 11 cross 11 cross 3, it's only seeing 11 cross 11 cross 11 cross 11 width times height part of the image. So these neurons are not at the first convolutional layer; these are higher up. They are seeing this much part of the image, and for this image, this neuron has the highest has the highest activation value. Okay. And so these researchers kind of plotted a bunch of neurons and which images activate them the most. Okay. I guess this is after the pooling or before the pooling or something like that. Yeah, there are 5 pooling layers. So you can see that there are some neurons which are getting activated for highly. So they are the most activated for when they see numbers. There are some neurons which get activated for faces, some neurons for some other things, and so on. So there are basically some neurons which are getting activated for some patterns and not others, basically. So this is also not very good story because I picked a neuron. There are many neurons in my CNN, and I know that maybe some image activates it really well. But what's the insight? This early work was not able to give too much intuition. So later on work also tried to do the same thing, but in a slightly different way. What it said was, I'm going to start with some random image, which basically is every pixel is a random value. Okay, which is this thing, and then I'm going to try to find a synthetic image which is going to activate a neuron the most. I'm still going to pick a neuron in my trained CNN. I'm going to pick a neuron. I'm going to start with a random image, and I'm going to slowly try to modify this image and figure out an image such that it activates that neuron the most. Okay, that will give me some idea about whether that neuron is detecting birds versus humans versus something else, and so on, right? So if you actually do that, like perturb this image slowly such that you find an image which activates, which gives the highest activation value for that neuron, this operation is actually should click to you as some sort of a gradient descent or gradient ascent, right? So there you pick a neuron, you forward propagate and figure out what the activation is, and you back propagate to kind of update this image. So this image is your parameter now. Just a connection there, but otherwise these guys were trying to do is to start with a random image and try to see what's the image which is exciting that neuron, basically. Okay, which did not work that well. So they start seeing with something called natural image priors. And so they start seeing some discernible patterns. Okay, which is which is something like this. For so they pick some neuron. Okay, it's they just saw that this neuron gets activated when this synthetic image resembles something like this, and they kind of eyeball it as it looks like a goose. Okay, many like. different positions and so on. And this neuron gets activated for the synthetic image, which has maybe an ostrich looking like this, looking like that, and so on. Okay, and they kind of do that for all their layers. So I guess this is not an LX net. This is a different net which has eight convolutional layers. I'm not sure if this is the last one is actually a fully connected layer or not. But you're basically picking some neurons and trying to see how which synthetic image kind of excites that neuron the most, right? So why is the size of the blocks increasing? Because the further away the neuron is, the larger the field it sees, right? If the neuron is in the first convolutional layer, it will only see the 11 cross 11 size of the image. If the neuron is towards the end, because of convolution spoolings, its receptive field, effective receptive field, because its local receptive field will be just whatever 3 cross 3. But if you kind of propagate it to next level, it's going to be maybe higher, 5 cross 5, 7 cross 7, and so on. So that's why these blocks are bigger. So you can see what types of patterns make that neuron activate the most. So these guys did a study, which is getting uploaded, yasinski.com/deepbiz. Okay, so that's visualizing synthetic images, and it's actually quite a interesting paper. Then the next fourth approach is about, okay, I don't know what my CNN is doing, but it's doing good classification. So maybe there's some other way I can try to understand how the CNN's performance is, in the sense of how is the CNN doing good classification. We know that the input is images, output is scores. So let's take the input to the layer that computes the scores. Okay, we know that scores is W times max of whatever the input was, because it's a multi-layer neural network. There is some input to this layer. This score computation, which is the activations of some previous layer, right? It could be a fully connected layer, which is passing through a non-linearity and then getting multiplied with W and D, right? So these are the activations. I'm just going to think of the activation A as a representation of the input image. What do I mean by that? I know that I was going from, let's say, 32 cross 32 cross 3 to 10-dimensional score vector, let's say, in the CIFAR 10 example. Instead of the 10-dimensional score vector, I'll backtrack one level and I'll get a different vector, different activation vector. I'm just calling it an activation, right? That need not be 10-dimensional. In fact, for example, in AlexNet, it's a 4096 dimensional vector, okay, which is ultimately getting to a 1000-dimensional score vector. In AlexNet, we have 1000 classes, so we're going from the final output is a 1000-dimensional score vector in AlexNet, right? But the one layer before that is actually a fully connected network whose number of neurons is 4096. Okay, that's why the activation is going to be 4096 dimensional vector. Okay, we can think of this activation. So I can pass an image and get this activation vector, and I can call that activation vector to be a representation of that image. Right? And then I can get these vectors and I can embed them into a two-dimensional space such that the distance properties are preserved. If you remember PCA, right? If you have a large dimensional data, you want to visualize some two-dimensional, three-dimensional version of it, PCA will help you do that, right? Something similar to that. I have a large 4096 dimensional vector. I can project it into a two-dimensional space and look at it. And so somebody plotted that. So A is 4096 dimensional. They plotted it in a 2D space. Okay, so some transformation of A falls at different locations here, and then they just put back the image that kind of corresponds to that A. So that's why they've kind of created a collage of images. And what they want us to kind of infer is that images which are next to each other are actually class based and semantic rather than color and pixel based. Actually, this is too low resolution for us to kind of eyeball that, but you can look at the link and kind of eyeball that. The pictures may have very different colors and pixel values may be different, but if they're semantically, let's say they represent let's say cup or something, they all belong to the same area. Okay, which means that the representations learned for the images were were good for classifying or putting them together. Okay. And the final thing that I want to discuss is visualization by occlusion. So okay, I have an image. I got it classified as a cat. Okay, but why did the CNN classify that as a cat? Okay, I'm not sure. So to figure out which part of the image is leading to a certain classification, I kind of occlude the part of the image and see what is the classification now. In particular, I'm going to plot the probability of the class of interest, let's say probability that it's a cat, as a function of my occlusion. So think of this first column here. I have this occlusion. This is a gray thing. Okay, I know. Okay, this is a Pomeranian. So this is just plotting the probability that the input is a Pomeranian as a function of the where the occlusion is. Okay. What do I mean by that? See, whenever I give an input image, I get scores, right? Or equivalently, I get probabilities, right? If I can normalize them, they look like probabilities. So let's say I put the occlusion to the top left, and I pass the image through my CNN. I'll get one probability that this thing is a Pomeranian, right? That's a number between 0, 1. I'll put that number there. I'll move the occlusion again, slide to the right. Again, pass it to the CNN, get a probability that this is a Pomeranian, and again put that number there. And I put all the probability of Pomeranian numbers into that matrix. It's just a function of where the occlusion is. You can see that red means high and blue means low. You can see that the probability of the Pomeranian decreases heavily when this part is occluded. Okay. So it's just trying to understand why is the CNN working basically. Similarly with this, there's a dog here but two other people. But if you occlude the dog, then clearly you can't. The probability that it's a Afghan hound decreases quite a bit. But if you occlude here, in fact, the probability is increasing quite a bit because it's getting confused. I think if you don't occlude, probably I don't know. So we've covered up to this. So we have looked at convolutional networking in detail. Okay. And we've looked at visualizing CNNs a little bit to kind of, this is useful for trying to understand why your network is working, and also useful when you're training a network, right? Sometimes you're not sure what improvement you want to do, so you can diagnose using those 4 avenues that I mentioned. We're not going to look at jump starting today, which is essentially about reusing somebody else's network. In summary, CNNs are very effective for image-related applications. They are the state of the art. So hopefully in the next class we will actually run a state of the art network to see some good performance. They exploit specific properties of images like hierarchy, locality, and spatial invariance. And there are lots of design choices that have been empirically validated and intuitive, and still there is room for improvement, and that's why there are new networks being designed and so on. Okay, that's it for today. Thank you.